In this section, we're going to see how to calculate horizontal stresses according to the theory of linear elasticity, and particularly using the equations of isotropic elasticity. We already know how to calculate total vertical stress. The overburden is equal to the weight of all of the rock on top of a given site at a given depth. And mathematically, this is the integral of the bulk mass density times gravity as a function of depth. With that value and with pore pressure, we can calculate effective vertical stress. And we do need effective vertical stress because deformations depend on effective stresses and not on total stresses. So let's come back a little bit here into the notes, and we see this section in which it is explained that in order to apply either the compliance matrix or the stiffness matrix and calculate the strains as a function of stress, we need to use effective stresses. You may recall the example of being at the seafloor. At the seafloor, no matter what the depth is, the sediments are quite loose with high porosity, and the reason for that is that effective stress is zero. When you go deeper and deeper below the seafloor, effective stress starts to increase, and that's why the rocks get more and more compacted. That's because these are a function of effective stress. Deformation, compaction, they are a function of effective stress. All right, so now that we know that, let's come back to the procedure about how to calculate horizontal stress as a function of depth. The first thing that we're going to do is we're going to assume that we are in a site which is called tectonically passive. And what that means is that there are no strains in horizontal direction, for example, in direction 1 or in direction 2. And you can think of that case as an example for the case that occurs with sedimentation in a natural sedimentary basin in which sediments deposit over time and they pile on top of each other, and if you do not expect any significant strains horizontally, these sediments should just get more and more compacted just in one direction, and that will be the vertical direction. In this case, we can apply what is called these uni-axial strain conditions because we just have strain in one direction. We're going to see later on that this also applies for reservoirs that suffer depletion. All right, so let's come back here to the theory, but remember these are the main conditions, that two linear strains, horizontal strains are zero, and one is different than zero. All right, so we're going to use the equations of stiffness, particularly the stiffness matrix. And let me come back quickly through that because I have skipped through that step in here. Here we are. This is the stiffness matrix. And what we do in this case is we make this epsilon 11 and epsilon 22 equal to 0, assuming that direction 3 is vertical. And also I make this epsilon 12 and epsilon 13 and epsilon 23 equal to 0 because I also assume there is no shear strain. As a result, for this value which is non-zero, I'm going to be able to solve for sigma 1, sigma 2, and sigma 3 as a function of epsilon 3. That's going to be my only variable. All right, so let me come back to the equations. You can go through the math for that, and you will find out that sigma 11 and sigma 22 are going to depend on the Young modulus and the Poisson ratio and epsilon 3. And sigma 3 or the vertical stress, it's also going to depend on the material properties and the amount of deformation in the vertical direction. Particularly from here, I like that you notice that now we can calculate the horizontal stresses sigma 11 and sigma 22 effective as a function of the effective vertical stress sigma 3 because we can replace here epsilon 3 for its function as a function of sigma 3, So combining these two equations, I arrive to this next equation that tells me that the effective horizontal stresses are proportional to the effective vertical stress to a coefficient which in particular for this theory is the Poisson ratio divided 1 minus Poisson ratio. This term is what is called the effective lateral stress coefficient. And as we can see, for these particular conditions, it's just a function of the Poisson ratio. All right, so let's try to see some typical Poisson ratios and what is this effective lateral stress coefficient. Here you have a plot of the effective lateral stress coefficient as a function of Poisson ratio. For typical rocks in which the Poisson ratio is about 0.25, sometimes a little bit larger, sometimes less, we see that the effective lateral stress coefficient is about 1/3. And what that means is that the effective lateral stress is going to be 1/3 of the effective vertical stress. Let's see the case where the Poisson ratio approaches 0.5. If you remember from solid mechanics, that means that we are reaching or we're getting closer to a solid which we could say is nearly incompressible or it doesn't have any shear strength. In that case, when the Poisson ratio approaches to 0.5, the effective lateral stress coefficient approaches 1. And this is very important because what this is telling you is that the higher the capacity of the rocks to expand sideways, which is the Poisson ratio, the higher the effective lateral stress coefficient is going to be. And we could also think about this in terms of how much the Earth is pushing sideways. When the Poisson ratio is high, the Earth pushes sideways with all its weight, to the limit in which even the horizontal stress is going to be the same than the vertical stress. However, for solids that have a smaller Poisson ratio, then that pushing sideways of rocks and sediments decreases, and decreases proportionally to the decrease in the Poisson ratio. There are some types of rocks, like for example salt rocks or soft mud rocks, which are not really linear elastic, are more what we can call viscoelastic, and they deform as a function of time, but they can present what it's called an effective Poisson ratio that approaches 0.5. And in this type of sediments, we do see that this effective lateral stress coefficient, it tends to be quite high. For other well-cemented rocks like a carbonate, like a dolomite, this coefficient tends to be smaller. All right, so we know now what is the effective lateral stress for a given Poisson ratio in a tectonic passive environment according to the theory of linear isotropic elasticity. If we want to know the total horizontal stress, the only thing we have to do is to add pore pressure to that. Always remember that these equations for using linear elasticity are going to be valid if you are relating effective stresses. So if you want to calculate a total horizontal stress, you need to add pore pressure again. Let's come back to the notes, and now we're going to use what we just learned in order to calculate the fracture gradient. The fracture gradient, now it's not a stress or a pressure, but it is a gradient. It's a variation of pressure as a function of depth. And we already know this equation. Here we have total horizontal stress, which we know, as we said before, is the result of adding effective horizontal stress and pore pressure. But now we have an equation for effective horizontal stress, which depends on the Poisson ratio and effective vertical stress. And we know that effective vertical stress is total vertical stress minus the pore pressure. So I can do a little bit of math and rearrange all of these terms and just put two terms as a function of the total vertical stress and the pore pressure, and we'll see that in front of that I'm going to have functions of the Poisson ratio. And I can go a little bit further and take the derivative of the total horizontal stress with respect to depth, and this is going to be the gradient of the minimum horizontal stress, also known as the fracture gradient, because that's going to be the minimum pressure needed in order to open a hydraulic fracture. And just by doing a little bit of math, we see that this is a very simple derivative. So here, uh, the Poisson ratios are material parameters, so they are a constant. So this is just going to be the derivative of the total vertical stress, and the same thing with pore pressure. So at the end of the day, now I can calculate what is the fracture gradient if I know what is the lithostatic gradient and the pore pressure gradient. We have already seen that these two gradients can be calculated for conditions, typical conditions with hydrostatic pore pressure. The lithostatic gradient is usually about 1 psi per foot. In hydrostatic conditions, the pore pressure gradient is about 0.44. And let me add one more thing here. The Poisson ratio is 0.25. In that case, the fracture gradient is 0.63. And this is something very important because this is telling you right away what is the minimum pressure, bottom hole pressure required to do a hydraulic fracture as a function of depth. You just multiply depth times this number and you will get it, as long as this site has these parameters and a Poisson ratio of the rock equal to 0.25. So I have one schematic about here the fracture gradient. Imagine that we are at a place with a depth of 10,000 feet. It's a tectonically passive environment with no tectonic strains. We're going to see what that is in a little bit, but that means that there is no deformation in the horizontal direction. We know that that's going to go and that's going to lead into a normal faulting environment. So if I want to calculate what is the minimum bottom hole pressure to do a hydraulic fracture and also to design my pumps on the surface, I can use what we just did, multiply the fracture gradient times the depth, and that's going to give me that particular value of horizontal stress at this depth. And now we can add to our list of values to remember 0.63. Remember, then the pore pressure gradient in hydrostatic condition is 0.44 psi per foot. The gradient of overburden or lithostatic stress or total vertical stress is 1 psi per foot, more or less in onshore conditions. And now we have added a new value, which is a fracture gradient, which is typically in the order of 0.63 psi per foot, and sometimes can be larger, 0.7, 0.8, depends on the site. But more or less it's going to be at least 0.63. Okay, so now that we have this theory, again, I want to emphasize that what we have assumed, this new theory that we have learned about linear elasticity and isotropy, allowed us to calculate horizontal stress. And this is something very important because that's something that we want to know in the subsurface for geomechanics, for several applications, not only for hydraulic fracturing. All right, let's now relax a little bit these boundary conditions in which I assume that there are no horizontal strains. What about if I do have horizontal strains? If I'm close to a tectonic plate and I do have large horizontal stress as a result of a shortening of the air crust in horizontal direction. All right, in that case, what I'm going to have to do is I'm going to have to come back to my stiffness matrix and now assume that epsilon 11, epsilon 22 are not zero anymore. So now these three linear strains are not zero. And I can write equations of sigma 11, sigma 22, sigma 33 do a little bit of math so that I can organize my equations as a function of sigma 33 and epsilon 11, and this is going to be the result. The result is going to be that the effective horizontal stresses are going to be a function of the effective vertical stress through the effective lateral stress coefficient, but also are going to be functions of the tectonic strains. Epsilon 1 and epsilon 2 are what we're called tectonic strains, and they quantify how much shortening or extension we have in the Earth's crust at a particular place due to the action of tectonic movement and tectonic plates. Let's do this a little bit simpler and talk in terms of horizontal stresses instead of sigma 11 and sigma 22. And this is the equation. Let me click here so I start launching this application. It's a little code that I wrote, interactive, that actually we have already seen, but we're going to look at it again, in which the only thing I'm doing is I'm just coding this equation and showing what is the effect of the Poisson ratio and the tectonic strains on the horizontal stresses at the given site. So with these equations, I can calculate effective horizontal stresses. If I add pore pressure, I get the total horizontal stresses. And here in this problem, well, it's the problem, it's over here, problem 344, but right before that, you have the general workflow that you have to follow in order to calculate horizontal stress. Let me go through that very quickly until we wait that this code starts running. First of all, always calculate total vertical stress. Second, calculate pore pressure or measure pore pressure. Sometimes, if we know the place is hydrostatic, we just can use this gradient. Some other times, if it's not hydrostatic, we have also learned the method that uses shell porosity in order to calculate that pore pressure. Or some other times, we might be given the overpressure parameter directly, and with that, we just calculate the pore pressure from the overpressure parameter and the total vertical stress. Next, I do have total vertical stress and pore pressure, so I can calculate effective vertical stress. With that effective vertical stress, and knowing what are the tectonic strains, whether they are zero or not, I can apply the method that we have just seen. Here I'm adding two other cases which we haven't seen yet, but I just wanted to emphasize that this method, this workflow, is general. It's valid for any constitutive relationship that you are using. In our case, we're using the first one, linear isotropic elasticity. After you get your effective horizontal stresses, you add pore pressure, and now finally you have your total horizontal stresses. Okay, it looks this is good. Let me run this, and we're going to see what is the effect of Poisson ratio and tectonic strains. All right, so this is an interactive plot, an interactive code, in which again the only thing I did was to code these equations to calculate horizontal stress as a function of vertical effective stress. All right, let's see what is the original condition. I have a Poisson ratio equal to 0. This doesn't exist in normal conditions, but I do have it here set to 0. And I have no tectonic strains, epsilon 11 and epsilon 22. All right, because of gravity, vertical stress increases with depth, and also pore pressure increases with depth, according to the gradients of 1 psi per foot and 0.44 psi per foot. However, look at the horizontal stresses. Horizontal stresses, S11 and S22, are exactly equal to the pore pressure, because the effective horizontal stress is 0, because the Poisson ratio is 0. As soon as I start increasing a little bit the Poisson ratio, let's put it at 0.25, horizontal stresses are going to start to increase. And in this case, the two of them, S11 and S22, are collapsing in the same line. And the effective horizontal stress, which is the difference between this dashed line and the blue line, is 1/3 of the effective vertical stress, which is the difference between the red line and the blue one, the vertical stress and the pore pressure. So you can see that this dashed line is about 1/3 of the way from going from the blue line to the red one. Let's now add a little bit of tectonic strains. Let's start in direction number 2. If I add a tectonic strain in direction number 2, then the horizontal stress in direction number 2 should increase. And this is what we see over here. Now we have two different effective horizontal stresses, and in general 3 different effective stresses if I include the vertical. If the tectonic strains keep on increasing, then I might have a case in which I jump from one of the horizontal stresses being higher than the vertical stress, and we saw this is the case of strike-slip faulting regime. If I add more compression on the other side, I can have the two of them being higher than the vertical stress, and this is what we know as reverse faulting stress regime. You can explain all of this as a function of these tectonic strains. One more thing I'd like to emphasize here, let's wait that these tectonic strains, they come back to the value that they should be with 0 tectonic strain. Okay, it is that with this theory, remember that we calculate effective stresses, and the effective stress depends on the effective vertical stress. The dashed line, if I have a Poisson ratio of about 0.25, we say it's going to be about at 1/3 of the way going from the pore pressure line to the total vertical stress line. And if I had a higher pore pressure that deviates from hydrostatic, that's still going to be the case. So you see now that in this case we have an overpressure formation with a pore pressure higher than the hydrostatic value, but still the relationship is still the same. The dashed line is about 1/3 going from the pore pressure line to the total vertical stress line. Okay, so we have covered almost everything that I wanted to discuss about total horizontal stress calculation with the theory of elasticity. Here you have one more example to calculate this total horizontal stress for a given site, for a shale. And again, you use all these equations and you get that value right away. There is just one more thing I'd like to mention, is that this method, although it is very simple, and sometimes it doesn't include many real processes that happen in nature. In many places it gives surprisingly good results. And here we have a paper that shows an example about that, in which in many places in the North Sea this method has been shown to do very well. Again, it doesn't mean that the physics of the method is correct, but it does give good values because it takes into account what we are mentioning and seeing that this effective Poisson ratio and the capacity of some of these rocks to expand sideways. So here, this is what we have seen, how to calculate the Poisson ratio. They go a little bit a step further. That's something we're going to do later on, to calculate the Poisson ratio based on wave velocities. But the result at the end of the day is the effective lateral stress coefficient, also known sometimes as K0, as a function of depth with a model. This is the green line, and what is measured in the field with Likov test. We see that the model in this case it does it yields very good and reasonable estimations.